Good morning. We will do a quick torque calculation example, and then we'll talk a little bit about angular momentum. We'll start off with this okay, we've got a meter stick. It's supported at its center point, 50 centimeter mark. If we hang 55 grams at the 75 centimeter mark, how many grams should we put at the 25 centimeter mark to keep the system in equilibrium? Okay, this one's easy. Let's go ahead and formally work it out, because we're going to have examples that aren't as straightforward. I'll draw a free body diagram. My stick, I've got some kind of a support force there, right? I've got some amount of weight over here and something over here, 55. Now I know grams is not a unit of force. I have to convert it to kilograms and multiply it by G. But my equation, if I have grams everywhere in my equation, then I can multiply by G, divide by G, it's the same thing, right? So I'm just going to leave it as grams. And I'm going to say the sum of the torque has to be 0 because it's in equilibrium. Remember, what did equilibrium mean up until 2 weeks ago? Up until 2 weeks ago, it was no net force. And now what does it mean? No net force and no net torque, right? Let's make that a red box. Our definition of equilibrium changed a little bit because now things can rotate. So we have to be a little more clear. So if I know this object, this meter stick is balanced, it's just hanging there, not rotating, not moving, I know it's in equilibrium. The sum of the torque has to be 0. Pick a direction as positive, it doesn't matter. I'll go counterclockwise as positive. So the torque is force times lever arm. The force produced by my unknown weight over here, X, multiplied by the lever arm, I'll call that lever arm D1, minus the force produced by the 55 multiplied by its lever arm, and both of those lever arms are 25 centimeters. So X is 55 grams. What just happened? Why do things disappear? Okay, let's see. Okay, we can fast forward there. There's our weight hanging at the 75 centimeter mark, and there's one at the 25 centimeter mark, and those two weights are the same. So what do we get here? 55 grams. Because the lever arms are the same, we need the same amount of weight on each side, the same force on each side. Okay? Let's make it a little more interesting. Let's do this one. Same meter stick hanging at the same place. 25 grams are hanging at the 90 centimeter mark. How many grams at the 40 centimeter mark to keep the system in equilibrium? And just go through, do me a favor, go through the calculation, even if you can kind of spot this and do it in your head. Oh, the screen's not looking good. Did you draw a free body diagram? And so what do we get? $100 grams. We good with that? Let's see. So there I've got 25 at the 90 centimeter mark. And look, you can see that one's much heavier at the 40 centimeter mark. Okay, got a good visual. Let's do this one now. $145-gram meter stick suspended at the 25 centimeter mark. How many grams do we add at the 0 centimeter mark to keep the system in equilibrium? This one's a little more interesting, isn't it? Let's go back up to the previous one. Over here, let me draw a more accurate free body diagram. What am I missing? We're missing the weight. So where would we put the weight? At the center of mass. We use center of mass really just for two things. The torque caused by gravity, it's basically the average force of gravity on our whole object, excuse me, is as if we put all the mass at the center of mass. The torque caused by gravity, we use center of mass, and gravitational potential energy. When something moves up or down, we want to know something with dimension, right? Moves up or down like a pendulum swinging down. We want to know how the gravitational potential energy changes. We've put all the mass at the center of mass, and we look and see how the height of the center of mass changed. So I'm going to put all the mass of my rod at the center of mass for this purpose. And then what do? Then I say the sum of the torque is I have 100 multiplied by 10 centimeters plus F support multiplied by what? Why didn't I include the support force earlier? Because it has a lever arm of 0. That is correct. So it produces no torque. The support force doesn't cause this thing to rotate, right? It does not change the rotation of the object. And how about the weight? It also has no lever arm. It acts right through the axis of rotation. So that's why I left it off earlier. But to be correct, I could have done this, included it like this. And then I have this minus 25 times 40 centimeters. Okay. Now that you saw that, can you do this one? So what do? I replace my meter stick that has a mass of 145 grams. I replace it with a massless meter stick and a weight hanging at the center of mass equal to 145 grams. So I say the sum of the torque has to equal 0. Doesn't matter what direction you pick as positive. I'll go counterclockwise. So I've got x times d1 plus the support force times 0, right? It does not produce, I could leave that out, right? But I'm just being clear here. Minus 145 times 25 centimeters. Oh, here, I'm sorry, D2. I'm jumping ahead of myself. So this is X times, what is that? 25 centimeters. And this is 145 times 25 centimeters. So X is why does it do that? Okay. Let's see it. There's the 25 centimeter mark I'm hanging it from. You can see that this won't stay in equilibrium by itself, but put 145 grams over there, and it does. So we can put all the mass of the meter stick at the center mass. We replace this meter stick with a massless meter stick and put a weight at the center of mass equal to the mass of the stick. As far as torque is concerned, that is acceptable. Yeah, we're replacing our meter stick, which has a mass of 145 grams, with a massless meter stick with a weight equal to 145 grams hanging at the center of mass of the stick. It's the same thing as far as torque is concerned. Now, you can't do that with rotational inertia. That does not work with rotational inertia. It works with torque caused by gravity and gravitational potential energy. And that's about it. How about this one? We've got our meter stick suspended at the 5 centimeter mark. We've got 5 grams hanging at the 75 centimeter mark. How many grams at the 0.4 centimeter mark to keep the system in equilibrium? I think you're forgetting something. There we go. All right, what do we have? We've got some unknown amount of weight times D1 minus 145 times D2 minus 5 times D3 equals 0. We get everything here? D1 is 4.6. D2 is 45. And D3 is 70 centimeters. We good? I can't hang something at 0 centimeters, right? I can't hang it at 0 centimeters. And back here, for this previous one, I just said it was at 0 centimeters because it doesn't make very much difference there. It's only 145 grams, right? But this makes a huge difference. In other words, 0.4 centimeters out of 25 is not a big percentage error, right? But 0.4 centimeters out of 5 centimeters is a big percentage error. It would change your value quite a bit. As you saw, you got 1,300 something and it's 1,500, almost 1,500. So that's why you have to be, on this one, we have to be a little more precise with where I'm hanging that weight. Okay, we okay with this one? Should we see if it works? So just a little 5-gram weight out there in the stick. And what do I need on the other side? I need this massive weight. 1,500 grams on one side to balance that. Now 1,500 is a little bit more, right, than what I needed, but close enough. All right. And does that remind you of anything? Well, let's go back. Let's go back. Does that remind you of anything? These construction cranes, right, have that similar look to them. This guy on the right side, it moves back and forth, right? It moves and it's lifting weight up and down. And this counterweight over here, it moves a tiny bit back and forth. When the other one moves a big distance back and forth, it moves a tiny bit back and forth, and it keeps everything balanced so that this crane doesn't topple over. Any force that does not pass through the support point will produce torque. So if the weight doesn't pass through, the line of force from the weight doesn't pass through the support point, then yeah, you have to take it into account. All right. Okay, we did that. Angular momentum. We need to get a little start on angular momentum. All right. Sum of the forces equals ma. What is a? It's the rate of change of the velocity, right? dv dt. If the mass is constant, we can bring it inside and say d dt of the quantity m times v. That's momentum. So the sum of the forces, and actually, this is the way Newton wrote. Newton didn't write sum of the forces equals ma. Newton wrote sum of the forces is dp dt. It's true even if the mass is not constant. So what we're going to do, manipulate this a little bit. We could do r cross both sides. And what we end up with is torque. This is torque on this side, net torque. R cross F is torque. R is the location to where the force is being applied. And we get d dt of R cross P. So remember what we said up here. We said if there was no net force acting on something, right? If there's no net force acting on something, then there's something special about this quantity mv. It does not change in time. Its time rate of change is 0. So that was, Newton noticed this and said, wow, this is special. When there's no net force, this thing can't change in time, right? It's something special about it. It's constant. And that's very useful to solve problems. Well, now we're saying we've got a similar relationship here, and we're going to say if there's no net torque acting on something, if the net torque is 0, then there's something special about this quantity R cross P. It cannot change in time. Let's give it a special name. Let's call it angular momentum, capital L. All right, so angular momentum, we have two formulas we use. This is one of them. When do we use this? When an object is moving in a straight line. And we have our other formula. What is this one? How do we get from translational linear momentum to angular momentum? Linear momentum is what? mv. So angular momentum would be, what do we expect it to be? Instead of m, we would have our rotational inertia I. And instead of v, we would have our angular velocity omega. And we use this formula for rotating objects. Okay. All right, let's see why we have these two. We're looking top-down view. We're at the park, looking down from our drone, right? A top-down view, and there's one of those merry-go-round platforms there that rotates. And we got a kid over here. Kid's going to run and jump onto the disc. No, it's not moving initially. But after the kid jumps on it, this is our initial state, right? After the kid jumps on it, what happens? It rotates. So the question is, can we use energy to solve this problem? No. This is inelastic, right? Inelastic collision. We know when things stick together, our mechanical energy gets transformed into types that we can't account for, right? Can we use linear momentum? I should write E No. Why not? Right before the collision, there's lots of linear momentum, right? The kid's running really fast. Just ask him, he'll tell you he's running really fast. Then they jump onto the merry-go-round, and then nothing is moving in that direction anymore because the merry-go-round is attached to the earth. The earth gets in the way. Nothing's going to get that disc moving. It's attached to the earth. But what can we use? The disc is free to rotate on that axis of rotation. It's mounted on something that's free to rotate. So there's no external torque acting on our system. The disc is free to rotate. When the kid jumps on it, we can use angular momentum. That means, what does that mean? Let's go back and look one more time at this situation. At the end, does this system have angular momentum? Yes, it does. Right, we've got something rotating, and angular momentum is I omega. There's certainly rotational inertia there. A disc has rotational inertia. A kid has rotational inertia. And it's rotating. There's omega. So there's angular momentum at the end. That means there must be angular momentum at the beginning. But that disc isn't rotating. And the kid is just running in a straight line. The kid running in a straight line must have angular momentum. Let's take a closer look at that. The reason is that if the kid collides with the merry-go-round, the system starts to rotate. So therefore, the kid has to have angular momentum before the collision. Let's look at this example. Kid runs, jumps, lands on the merry-go-round right here. Does the merry-go-round start rotating? No. So in this case, the kid running in a straight line did not have angular momentum. But in this case, the kid running in a straight line. I'm just going to copy this. Oops, what happened? Kid running in a straight line does have angular momentum. There we go. All right, let's take a look. Now we're going to use, remember I said there's two formulas. Where are my formulas? Big red box. For an object rotating, I omega. That's how we calculate the angular momentum for an object rotating. For an object moving in a straight line, it's R cross P. Let's take a look at that. Let's figure out how to find the angular momentum of the kid running in a straight line. So we have an object moving. Man, I cannot write today. This is our axis of rotation. We already saw up here that the motion has to be relative to some axis of rotation. It changes, right? In one case, the kid had angular momentum. In another case, the kid didn't, right? So it somehow depended on how their motion corresponded to the axis of rotation. Let's pick this as our axis of rotation. We'll call this D perpendicular. How about? Oh, I didn't leave enough room. Let me. Yeah, kind of. That's. I guess that'll work. All right. So, what do I have? I've got R. R is this vector here. From the mass, from the object to the axis of rotation. That's the vector R that I've been using here today. We'll call this angle phi. Sorry, I've got, this is from the axis of rotation to, not this way, from the axis of rotation to M. R points this way. Let me put a big arrow on that. From the axis of rotation to our object. All right, L is R cross P. That's the magnitude of R, the magnitude of the momentum times the sine of the angle you get when you put their tails together. So when I move this vector R out to here, let's put their tails together. I get this. I get this as theta. Right? Theta is the angle you get when you put the tails together of R, and V, or the momentum. So let me work through this real quickly. What do I have? R is just going to be R. The momentum is mass times velocity. And theta is 180 minus phi. We see that? And the sine of 180 minus phi is the same as the sine of phi. And so this is mv, which is the momentum, times r sine phi. And r sine phi is d perpendicular. The perpendicular distance from the line of the momentum, that's this line right here. What color should I use? The line of the momentum, the perpendicular distance from that line to the axis of rotation times the momentum gives us the angular momentum. So you could see in this case, d perpendicular is 0. The line of the momentum passes right through the axis of rotation. In this case, we get angular momentum, not 0. The line of the momentum does not pass through the axis of rotation. This is the way I like to remember it. It's the momentum times d perpendicular. Okay. And the direction is given by the right-hand rule. So if C is equal to A cross B, the magnitude of C is the magnitude of A. We already wrote this out. The magnitude of B times the sine of the angle you get when you put their tails together. So A would be this vector, and B would be this one, and that would be theta right there. This angle you get when you put their tails together. And the direction you get from the right-hand rule. I put my fingers in the direction of the first vector, and I kind of roll them toward the second vector, and my thumb points along the axis of rotation, and that's the direction of the cross product. So in this case, the cross product would be between A and B, like this, would be out of the page. And if I reverse the order, if I say B cross A, then it reverses the direction of the vector, right? So that would be B cross A would be into the page. A cross B is out of the page. So pick a right hand. Some people use 3 orthogonal fingers like this for their right hand rule. I put my fingers and then I kind of roll them toward the second vector and my thumb points along the other one. They're all different methods for right hand rules. Just make sure you use your right hand. If you're like me, you're right-handed, and you're holding your pencil in your right hand, and you're feverishly working your physics problem, and you don't want to take the time to put your pencil down, don't use your left hand. Just put the pencil down, use your right hand. If you're left-handed, you've got an advantage here. The first vector is this one. So if I said D is equal to B cross A, you have to write it in the right order. Then D is into the page, and D is equal to the opposite of C. Magnitude's the same, direction is different. Okay, I'm going to stop the recording, but I'll stick around for our review session.